Hello, everyone. Welcome to the CIERA Spotlight series. My name is Gideon McFarland. I'm a graduate student here at Northwestern, and I'm joined by Lindsey Kwok.
Hello.
Lindsey is a postdoc researcher on the Hubble Fellowship, and she's here at CIERA studying the astrophysical origins of exploding white dwarf stars using spectroscopy from the James Webb Space Telescope. Welcome, Lindsey.
Thank you so much for having me.
I want to talk about some of the jargon we'll be talking about today.
Okay.
Because in that introduction, there was a lot of jargon words. Maybe we can break down some of them.
Definitely.
So for instance, white dwarfs, exploding white dwarfs. What is a white dwarf, first of all?
Okay, a white dwarf is kind of the end state of an average-sized star. So our sun, for example, will eventually become a white dwarf. It's like the carbon and oxygen core. You can think of, for a size scale of the white dwarf, you're taking something with the mass of the sun and you're squeezing it down into something the size of the Earth. So these things are really, really dense. It's not fusing hydrogen and helium in its core anymore. It's actually held up from gravitational collapse by pressure called electron degeneracy pressure. Basically, those electrons just don't want to be too close together.
Yeah, these white dwarfs are really interesting objects, very compact, very dense. But of course, they also explode, and I believe we call that a supernova. It's a specific type of supernova, right? A type 1A supernova?
Yeah, so they're often called type 1As. Supernovae are classified based on their spectra, and these spectra don't show hydrogen or helium, which makes them 1As. Basically, what's happening is it's a thermonuclear explosion of a white dwarf, which is a different kind of supernova than what a lot of people typically think of, where you have a massive star, basically core collapses and then rebounds and explodes. There's a different process going on.
So you mentioned spectra. We should also explain that.
Okay, yeah, so spectra are really valuable type of data that we can get of astronomical objects because they take the light from that object and they split it into its constituent wavelengths. It's basically like taking white light. When you split it through a prism, it turns into all the rainbow of colors. So the spectrum can tell you if there's absorption or emission at specific wavelengths. It can tell you if there's particular elements that are located in our supernova ejecta, and those help us understand how it exploded.
Okay, so these white dwarfs, they explode, type 1A supernova. But how does that explosion happen? What causes it? What triggers it?
Great question, and the answer is that we don't fully understand. We've been studying these objects for many decades. We're still resolving the details. The basics is that you need your white dwarf to be in a binary system of some kind. Our sun, as a white dwarf, will actually never explode. It will just fizzle out forever because it's not in a binary system. Our sun doesn't have a companion. So if you have a companion star, it can give mass to the white dwarf, build it up. And there's this theoretical limit called the Chandrasekhar mass limit. It's about 1.4 times the mass of our sun. And if you exceed this, electron degeneracy can no longer hold up the star, and it can trigger an explosion. This is one avenue to get a white dwarf to explode. This is usually the textbook single degenerate scenario where the white dwarf takes mass from some regular star and then explodes. But there's problems with this avenue, and actually we think another very promising scenario is you could have two white dwarfs, and these white dwarfs can be in a binary system, they're merging, in-spiraling, and then one or both could explode either through tidal disruption, or there's a little bit of helium on smaller white dwarfs that ignites more easily than carbon and oxygen, and this is called double degenerate scenario because there's two degenerate white dwarfs, but it can also explode in what's called like a double detonation. There's all these different kinds of ways that the white dwarf explodes, and we're trying to understand which kinds of these explosions cause the variety of thermonuclear things we see in this spectrum.
So we'll get into the science and your day-to-day research in a second, but before we get there, we want to understand how you got to where you are now.
Yeah.
And so could you just tell us a little bit more about your journey to astronomy, what got you interested in astro, and how you got here?
For sure. So as a kid, I started with an interest in science and math. These were things that I was good at, but also I have a grandfather who was a nuclear physicist, and I did not know what that meant when I was younger, but I knew he was the smartest person that I knew, and I wanted to be like him. And whenever he'd ask me, what do you want to be when you grew up? And I'm like, oh, an engineer maybe? He would always like give me a lot of positive reinforcement on that. I had no idea the difference between an engineer versus a scientist at that point in time. But in middle school decided, yeah, I want to be just like my grandpa and do nuclear physics. But then as a freshman in high school, I got to take a little introductory elective class on astronomy. I was like, wait a second, these stars and black holes and galaxies, this stuff's the cool stuff. And then I decided instead of nuclear physics, I wanted to do astrophysics. For some reason, that just stuck. When I did physics in high school, I really liked physics in general. And I never actually took another formal astro class till maybe junior year of college. The astronomy path always stuck. I've just been fascinated by these cosmic things that are just, they blow my mind, and that's why I want to know more about them.
Yeah. Was your grandfather disappointed that you you switched off of nuclear physics to astrophysics?
No, actually, not at all. He was very excited. I think he might have been a little disappointed if I'd switched to like the arts or something, but yeah, he was very supportive.
That's great.
Yeah.
And talking about that route, that path, were there any challenges you had to overcome getting to where you are today, or?
I've been very fortunate that I have had a lot of support along the way. My parents were always supportive of exploring STEM opportunities. I did a high school program during one of my summers where I applied and we tracked near-Earth asteroids throughout the summer. It was amazing, but they offered financial assistance for me able to do that. And then I went to Caltech for undergraduate, received a good amount of financial assistance there. But the people have always been the most supportive. I have had good mentors, getting me on good research projects, giving me experience, and that really led me from undergrad then to graduate school. I had an amazing advisor in graduate school, a very supportive family. Maybe something slightly unique. I think it should become more common if that's what people want for their lives. I had 2 children in graduate school, and so this transition to like having a lot of family responsibilities as well as work responsibilities was something that I definitely relied on the support of a lot of people to help me navigate through. Maybe navigating the whole family work balance with 2 careers in our family has been a very worthwhile challenge, but something that's taken some effort to figure out. Yeah.
Yeah, I imagine that balancing probably was very, very difficult, but it's great that you had.
Still something that I'm figuring out. It constantly evolves, but yeah.
Yeah, but I'm so glad you had a really good support system.
Makes a huge difference.
I'm wondering if maybe someone in that support system also drew you to CIERA, because you ended up here for your postdoc.
There's a lot of reasons to come to CIERA. I think it's an amazing community. One thing that's exciting for me as a postdoc here, there's a fairly large postdoc community, and sometimes at other departments there's a much smaller cohort of postdocs. I also think that everyone was super welcoming and friendly and worked with me to try to make sure some of those constraints were fulfilled, but it was just nice that people were willing to work with my situation. But there's a lot of also resources here at CIERA that have been helpful. Telescope access, a lot of people doing similar and complementary work to what I do. So yeah, all of those things were things that brought me here.
Yeah, great. So thank you for telling us a little bit more about your story, but now let's dive some more into your science.
Okay.
So we sort of explained a little bit how these white dwarfs explode and how you're studying these explosions. Can you tell us just a little bit more details of why do these explosions interest you? What are your general science interests, and why have they sort of focused around these exploding dwarf stars?
Good question. Simple answer is I've always been fascinated by like the wild stuff. Black holes, exploding stars. I don't know why, but these kinds of high energy phenomena are fascinating to me. Originally, I was really excited in black holes and things like LIGO, but it was very computational, and I decided that I really wanted to do something with data. So that's part of what drew me to supernovae. So I'm in a field that we call time domain astrophysics. Essentially, we're looking for sources in the sky that vary on very human timescales, things like seconds, minutes, hours, but supernovae vary on like days, weeks, months, years timescale. And that's very human, which makes the follow-up and the observing of it very fast-paced and exciting. I like that. You get new objects all the time, you follow them, you write them up, and then another weird thing comes along. So the actual work of what I do and what that work looks like makes a big difference to why I chose this field as well. I think there's a lot of interesting different science problems. And then beyond that, you kind of have to look for the opportunities as they come to you.
Could you say a little bit more about day-to-day? What is it that you do? So is it like every day you walk in and there's a new supernova you have to look at? Or is it more like just like typing on your computer? Like what is your day-to-day research like with this kind of fast-paced environment?
There's a transient alert system. Looking through those alerts, finding something interesting, asking people to get follow-up spectra of them. If it is a cool thing, then sending in that JWST trigger. Yeah, most day-to-day work is like on my laptop, coding in Python, Jupyter notebooks, trying to take the spectrum that I did observe and then analyze it to figure out what it means.
Awesome. Well, your science is really, really interesting, but of course a researcher is more than her research. So we also want to ask about your human side,
okay.
Sort of what you do outside of research. So what are your interests when you're not, coding or looking at white dwarfs exploding?
As I alluded to earlier, I have a family. I have actually 2 daughters. One's like 5 and one is almost 2. They keep me pretty busy outside of astronomy and exploding white dwarfs. A lot of my time goes that direction towards family, parenting, going on play dates, going to parks, hanging out, watching Disney princess movies, which is what I would be watching anyway, actually. I also like to read. I love fantasy. My family and I enjoy traveling. I really like the conference aspect of being an academic because I get to visit a whole lot of new places in several different countries.
And I understand you brought some things to show us of your interests.
I
So
did.
For instance, you brought a book you're reading right now.
Okay, so the book that I'm reading right now is called The Way of Kings by Brandon Sanderson. I've put this off for like 2 years because it's just too big to start, but I'm actually proud of myself for pacing myself this time. I highly recommend Brandon Sanderson to anyone who likes fantasy.
I love Brandon Sanderson.
You do?
I'm a fan. Yes.
Oh, awesome. Huge Harry Potter fan, and my daughter made this little beaded Hermione. It was pretty fun. It's always fun when they come home from school with little like handprint activities. Recently, my daughter came home from school singing Golden from K-pop Demon Hunters, and I've drawn this very cute picture of Rumi, and of course wanted the hair to go with it. So I figured out how to do Rumi hair. I was very proud of myself. I did this Monday of this week, so I had to show it off.
Yeah, well, thank you for showing us all the wonderful artwork in the book, for showing us all those. And we're going to end the interview pretty soon, but we have 2 more questions, fun, future-looking questions to ask you. So the first one of those is, what are your plans actually for the future? What are you looking forward to in the next few years?
Yeah, so like I talked about, I really love the research I do, but I also really love teaching. So my ultimate goal is to become a faculty member at a university where I can do both of those things, the teaching and the research. And then in terms of research in the future, I'm really hoping to get some more JWST data and programs to be able to explore and answer some of these unresolved questions. So I'm definitely excited that direction, but also looking for ways to expand more broadly towards other types of transients or different techniques to use to analyze our data and get even more information out of it.
Yeah, that's great. Well, this has all been wonderful hearing about you and your work, and we're looking forward to seeing where you go in the future. But our last question, which is a little more fun, not really sciencey. Let's say you're stranded on a deserted island, and for some reason, instead of trying to save yourself, you want to do some research. What is one tool you would want to have on that deserted, stranded island?
So suspension of disbelief, because
Yes.
if I'm stranded, I'm definitely not researching, but I would need my computer. I can't do research without my computer. That's a must. I assume there's not Wi-Fi?
No Wi-Fi,
Oh,
no electricity.
Oh no, so I just have until my computer battery dies.
Essentially, yes.
Ooh, rough. Well, if I get a second wish, then I just want a huge telescope, like the Keck telescopes in Hawaii, and I'm just going to take tons and tons of nebular spectra of transients. Presumably, I will have a list of those with me, including their coordinates on the sky. Yeah, exactly.
Amazing. I would never have thought to just have a giant telescope as my tool on my deserted island. That's a great answer. Yeah, thank you for being here, Lindsey. It's been great having you. And thank you everyone at home for watching this interview, and we'll see you next time. Bye-bye.